Good afternoon, good morning, probably good evening. My name is Ruslan Milentiev. I'm a postdoc here with Julie Binot at KAUST, and let's begin the section 4B. So yeah, welcome to the section 4B. It is the very last section of the last day of the KAUST workshop. The theme of this session is building the carbon-based industry. And the carbon-based industry is a very important concept in terms of Vision 2030. And we have 5 speakers to develop this concept. The first speaker is Dr. Wesley Cantwell, who is the Professor of Aerospace Engineering and the Director of the Aerospace Research and Innovation Center at Khalifa University. After receiving a PhD at Imperial College London, Professor Cantwell spent a decade at EPFL and another decade at University of Liverpool before settling at Khalifa University and establishing the Aerospace Research and Innovation Center in 2016. Today, Professor Cantwell will disclose their model of industry-university collaboration and how they consider to advance composite applications in aerospace industry. Please enjoy the presentation of Professor Cantwell.
Hello, my name is Wesley Cantwell and I'm at Khalifa University in Abu Dhabi. The title of my talk today is the Aerospace Research and Innovation Center, a model for industry-university collaboration in the UAE. For those of you that have not familiar with Khalifa University or Abu Dhabi, Abu Dhabi is a city in the United Arab Emirates. You can see up here in the map. Khalifa University itself is the main campus is situated downtown Abu Dhabi. Most of Abu Dhabi is here on this island you can see here. Our main campus is downtown. We have a second campus which is just off the island somewhere over here. Which used to be the Petroleum Institute, but we merged with the Petroleum Institute several years ago, and we are now one university. So the Aerospace Research and Innovation Center is located on the downtown campus here. You can see this is part of a new build that was completed 3 years ago, and it's a nice modern campus. The research center is actually in the older part of the campus behind these buildings. So a few words of introduction then about the research center. The agreement was signed at the Dubai Air Show way back in 2013. It was signed in the presence of a sheikh, and sitting at the table there you can see the senior manager from Mubadala Aerospace. Mubadala actually put up 50% of the funds for the research center, and Khalifa University funded the remaining 50%. And on the left-hand side there, you can see our president, our former president, Dr. Todd Lawson. So that was signed back in 2013. So the Research Center is funded 50% by Mubadala, which is an investment arm of the Abu Dhabi government, and also 50% by Khalifa University. And the aim of the center is to support a composites aerostructures called Strata, located in Al Ain, which is about 90 minutes drive from Abu Dhabi. Here you can see a photograph of the outside of the building, the first stage, which was built in 2009. I always tell people, particularly people who live here, it's one of the UAE's best kept secrets, because a lot of people are not aware of this facility. And you can see there in the right-hand picture, it's really quite a nice state-of-the-art facility where they do build to print of primary and secondary aerostructures for the leading aerospace companies. And they build a range of different structures. A lot of the earlier manufacturing focused on wing movables, things like flat track fairings, ailerons, spoilers, and but now they also manufacture parts for the vertical fin of the 777, also the Boeing 787 Dreamliner vertical fin, and they manufacture parts also for smaller companies like Pilatus. So it's quite an impressive manufacturing facility that they have built up here. To complement it, the work has recently been completed on what's called the Strata Solvay facility. It's an 8,500 square meter facility located very close to the Strata manufacturing plant. And they are producing carbon fiber prepregs here to supply Strata and satisfy their manufacturing needs and requirements. So this has recently been finished very close to Strata themselves. So let's go back to ARIC and talk about that. As I said, the agreement was signed in 2013. Our first challenge was really to find somewhere to locate it on the university campus. The decision was taken to house it on the university campus, but there really wasn't a suitable space. So we ended up having to take over this sort of undercroft area that you can see here. It's under one of these, under this large building here, over here in the corner. It was fully open, and this was a nice large open space that we took over. And over the space of about 18 months, we built the facility. You can see here the sort of entrance area in the main hall. This was completed in about middle of 2016, and you can see some of the equipment there in the center. This slide just gives you an example of some of the larger pieces of equipment in the center. Top left is our autoclave. It's a 1 by 2 meter autoclave that can go up to 400 degrees C, so we can process thermoplastic composites if necessary. Bottom left, we have a press we use as an RTM press. We have other presses as well. This is our X-ray computed tomography system for non-destructive testing. This bottom right is one of our robots. Now, the research in ARIC divides into two parts. We have materials and manufacturing is one stream of our activity. The other is automated manufacturing, including such things as automated drilling. So this is this is our large robot that we have in that area of activity. In the last couple of years, we've started to invest more in additive manufacturing, and you can see here on the right our metal additive manufacturing machine. It's an EOS 404, so it's got 400 watt lasers in it with a build volume equivalent to a 400 millimeter cube, and we build from aluminium, titanium, superalloys, and other metals. And on the right, we have one of our printers. It's a big rep printer, and there we can print structures up to 1 meter by 1 meter by 1 meter. So we can print molds and other useful bits of equipment in that using that printer. The governance of the research centre, we have a senior management board which comprises of 2 members from Khalifa University and 2 from the external stakeholder. We meet 4 times a year. At these meetings, we have to approve budgets and projects, and we discuss staffing requirements. So, you know, we do work closely with our stakeholders. And the way that we set up the research centre was we would send our research scientists to Strata to work with their engineers, and their engineers would spend quite a bit of time in the research centre. So we get this exchange of ideas and this close collaboration, and that feeds into defining the projects that we actually undertake within the Aerospace Research Centre. I have the very good fortune to work with many excellent colleagues in the centre, and I've shown them here. On the top line are my colleagues that work primarily on materials, structures and manufacturing, and the bottom line of 5 colleagues are in the Robotics Institute, and they support us in the automation projects and the robotics projects. So a very good team of faculty members support our activities. Research projects, we've had many projects over the years, as you can imagine, and I've just listed some of our key areas of focus here. One of our earliest activities was resin transfer molding and vacuum assisted resin transfer molding. We were heavily engaged in that and still do quite a bit of work in that area. Process reduction and elimination in composite structures. Clearly, that's very important to industry and our industrial partner. Automated drilling of aircraft parts, vision-based robotic manufacturing, processing-induced deformations in composite structures. Again, it's another very important topic and issue for our stakeholders. You can see the photo there on the right-hand side. That's from this particular project. That U-shaped structure is the sort of simulator flat track fairing structure, and we had a 2-year project looking at spring in and spring out and trying to predict it in carbon fiber sandwich structures, and that was a very successful project. We have a project on thermoplastic composite structures. Thermoplastics is a growing interest once more in them. Additive manufacturing, as I mentioned, and at the bottom there I've put in scaling effects in composite structures and other structures as well, and that's an area that I've been particularly interested in for a number of years, and it's got relevance here. You know, we are looking at how we can scale up many of our activities to transfer them over to the industrial setting. And that's in part the way that the projects are focused. The aim is to bring the projects to a certain level of maturity and then hopefully transfer them over to our industrial partners, who will then work and further develop those activities. So that's sort of been the model that we have followed. I said that our activities divide into 2 parts. There's the automation and there's the materials and manufacturing. Just to say a few words about the automation and robotic manufacturing, we have had several projects in this area, and these are very important because Strata is very keen to introduce robotic technology into their workplace and replace manual labor, which of course has its hazards, health hazards, and other issues related to need to rework, structural damage, etc., etc. So we've been looking at using robots, and this particular project that I'm showing here is a project looking at vision-based robotic manufacturing using bio-inspired event cameras. So this is an ongoing project, and other projects in this area we had a large project that ran for almost 3 years on robotic drilling, and this is one of those projects that got to a certain level of maturity and then was transferred over to Strata. So we worked a lot on developing end effectors to undertake these drilling operations. The video there in the middle shows some of the activity from my colleagues on looking at robot mobility in the workplace, getting robots to navigate around the workplace and undertake certain key functions. And we're also working quite a lot on robotic sorting and pick and place technologies. So in the second part of this talk, I just wanted to talk briefly about some of the work that we've done on scaling. As I said, we work a lot with small structures, and the question we're often asked is, can you scale this technology up to larger structures? Started working on scaling many years ago. PhD supervisor John Morton was very interested in scaling, and then when I was at Liverpool University, Professor Norman Jones really done a lot of interesting work in this area. One of our earlier projects was on scaling of fiber metal laminates. FMLs are combinations of metal and composites, and in these scaling approaches, what we do is we accurately scale both the specimen and the test fixtures. So in the top left there, you can see some beams that were manufactured, FML beams, and you can see that the dimensions are accurately scaled, length, width, and thickness. We have 4 scaled sizes there. We call it quarter, half, 3/4, and 1. And not only do we need to scale the specimens, but we also need to accurately scale the test fixtures and all aspects of it, including crosshead displacement rate, etc. And we worked on this for quite a number of years in Liverpool. Here's some work that we did on low velocity impact on scaled fiber metal laminate panels. The figure on the left shows force displacement traces following low velocity impact on 4 scale sizes of panel. Clearly, you can see there's significant difference in the way these panels respond. The quarter scale panel here, very low force compared to a much larger impact force and displacement from the what we call the full scale prototype, or the n=1 sample. But if you scale these responses according to scaling laws, you would divide the force by the square of the scale size. I've mentioned scale sizes over here. So normalize the force in this way, normalize the displacement by dividing by the scale size. You find that all 4 traces collapse nicely, one on top of the other. So these very small quarter scale samples are accurately reflecting the response of the large panel. And you see that also in the failure modes here. You get very similar failure modes in the 4 scale sizes. So there's a lot of potential benefits from using this approach. Here at Khalifa University, we extended this to look at scaling in isogrid structures, not only in the mechanical properties, but also in the manufacturing of them. So these are 4 scale sizes of isogrid mold, all identical, just change the geometric parameters. Again, a quarter scale, half, 3/4, and 1. And we use vacuum-assisted resin transfer molding to manufacture isogrid structures using these molds. So we fill the grooves with composite, in this case carbon glass fiber, and then we infuse it. We look at the fill time here for the different sizes, and we compare that with predictions to see how if they fill as we would expect. And what we see here is that we do see discrepancy, certainly in the smallest size here. There are challenges when it comes to putting glass fibers in very small grooves like that. We work with woven fabrics and actually cutting them and putting them in the grooves and then putting a skin on top and infusing it. There are challenges, so we get into trouble here, but it worked pretty well thereafter. We got fairly good agreement between our predictions and our experiment. And also, if we look at the mechanical response of these isogrid structures, here again, it's our normalized force against normalized displacement. And given that we've got 4 very different sizes of structure, they normalize pretty well. As you'll see here, the one in blue, that's our quarter scale sample. There are challenges in making isogrids as small as that, and we can see up here in our fill time as well, there are some challenges. But putting that aside, there's fairly good agreement, certainly between the 3 larger sizes of scaled isogrid. We've moved to other types of structures as well. We were interested in these sort of metal curvilinear structures at one stage. It's called Metawell, and we were wondering if we could produce these out of composite material. This is carbon fiber reinforced composite curvilinear structures. Again, 4 scale sizes, put one on top of the other just for photographic purposes. This is a sort of a quick summary of how we made them. We make them in a single one-shot operation. So we bond them and cure them in the same operation. And we use steel tubes wrapped with a polymer film to give it a shape there. And we made carbon and glass fiber structures. And you see exactly the same types of failure mechanisms in the 4 scale sizes. So we've blown the photo up here of the quarter and half to the same sort of dimensions as the n=1. Very similar failure mechanisms. And also if we look at the scale force displacement, we get exactly the same type of response. Just in the last part of my talk then, I wanted to just say some more, talk about some more recent work on additive manufacturing. We used our big rep printer that you saw earlier on to look at scaling effects in 3D printed polymer structures, and we looked at simple cubes in compression and flexural beams. And then we went on to look at lattice structures, these types of lattice structures you can see here, BCC lattice structures, people commonly refer to them as, and we've again got 4 scale sizes. So this is about 20 millimeter size here on this smallest one, up to 80 millimeter here on this largest one. And the question is, do we get the same response from the small one as we do from the large one? There's our load displacement traces from the 4 sizes. Here's the quarter scale, half, 3/4, and the n=1. When we normalize them, we get reasonably good agreement. You can see here that this n=1 sample is somewhat higher, but the general response is somewhat similar. But where we do see great similarities is if we compare the failure modes and mechanisms. This is the n=1/4 sample under compression. This is the n=1, so this has got 64 times the amount of material. Took a lot longer to manufacture, but the failure modes are very similar in both sets of samples. So in the last part then, I just want to talk then about the how we've extended this to look at metal additively manufactured structures. We've done similar type of tests here. We did cubes, we did beams as well. This is a summary of some of the flexural tests we've done. Here are our scale sizes of beam following testing. Here are our scaled displacement traces. And you can see here that as we quite often see that the quarter scale sample is slightly below the others. And if you look at these samples after testing, you can see here that that's the quarter scale sample. Okay, the photograph has been magnified to give it the same sort of scale as the other samples. You can see here the surface finish now becomes quite important, and this may well be affecting our mechanical performance. But nevertheless, if you look at the failure mechanisms in the 4 scale sizes, they're pretty similar in all 4, and also the overall deformation is very similar, as well as the load displacement response. And Again, if you extend this then to look at more complex structures like lattice structures, so these are aluminium alloy lattice structures, 4 sizes there, all scaled accurately. We haven't put the top plates on them yet. These were added afterwards in a second operation. And on the right-hand side here, you can see brackets. We extended this work to sort of consider simple brackets. Could we start to look at more complex structures and see if we can use our scaling approaches there? In terms of the lattice structures, here you can see the initial force displacement response. Here you can see the normalized force displacement response, and all 4 curves seem to form largely one on top of the other. Again, the n=1/4 is slightly off here towards the end. But if you look at the failure mechanisms, you see that they're almost identical in all the scaled sizes. So we get very similar failure mechanisms and also similar mechanical response. And then in the last part, we considered the scaled brackets. So here are the brackets that I showed you earlier. We fixed them on a vertical frame. We loaded them at one end and loaded them to failure. Here are the force displacement traces. Maybe I should have moved that up there. And you can see here that force displacement traces the quarter, the half, and the n=1. We didn't do a 3/4 sample here. We scale them, we get reasonably similar response. The quarter is again slightly below that. But look at the failure mechanisms, very similar in the 3 different scale sizes. You can see where failure initiates, and it's very reproducible. So that's all I wanted to say, and I'll just close with a photo of Abu Dhabi, and I hope that you'll come and visit us in Abu Dhabi sometime. The sun always shines and the beaches are always glorious in Abu Dhabi. So at that point, I will close and say thank you very much.
Thank you very much. Thank you very much, Professor Cantwell. It was very informative and also very illustrative, especially the introduction to your lab and Khalifa University. I'm personally very motivated to see Khalifa University and maybe your lab once in future. When people reminded their questions, perhaps one for me. You mentioned it, fiber metal laminates.
Yeah.
As the application versus impact-induced damage of the aircraft structures. Is there a wider application for metallized polymers? For instance, metallic coating on polymers to insulate the fuselage for lightning strike protections, or what's the prospect for polymer metallization in the aircraft industry?
Well, I don't know. I focus primarily on fiber metal laminates, as you know. So that's not something that I really considered. We've just looked at these laminates for really structural and for energy absorption, most specifically blast. As to the specific answer to your question, I really couldn't answer that.
Thank you anyway.
Did you have a question for me from the comments or?
Yes. The anonymous attendee is very interested about the process-induced deformations. What kind of software have you used for the modeling?
Yeah, I guess talking about the spring back. Yeah, we had a project looking at spring in and spring back with our sponsors, because that's a very important issue. We were using Abacus Compro for that, and it gave us the stress fields, and it gave us accurate predictions of the degree of spring in. So it was Abacus Compro. For the other work that I mentioned early in my talk, it was on the VARTEM. We used PAM RTM in that case, but for the spring in, it was Abacus Compro.
Thank you. The one more question, do you produce a commercial grade of CFRP laminates for the general market?
Commercial grade, it depends really what the question is. We just produce laminates for research purposes. Our sponsors down the road at Strata, they do the serious manufacturing, but ours is purely for research purposes. Yeah.
Okay, just one more question for me. Years ago, I was involved in a project about drilling of CFRP, and I see that you have quite great facilities, and this problem is still alive, drilling of CFRP. Here at KAUST, we do adhesive bonding, and I thought that adhesive bonding already pull all the duet on itself, but I see that the drilling problem is still alive. What's the ratio of the adhesively bonded and drilled bonded CFRP composites in aircraft industry today?
Well, I don't want to give away too many of the trade secrets at our sponsors in Lausanne, but let's say that plenty of rivets are on display, and so it's you know, the good old-fashioned technology. Riveting, I think, is still quite widespread in the industry, but of course, adhesive bonding is used as well. As in terms of specific ratios, I don't have that information to hand.
No, but anyway, there is still a million holes in the Boeing 787, yeah, which need to be drilled.
Yeah, I guess it gives added confidence. Yeah,
sure. Thank you very much for
okay,
your being today here with us.
Thank you.